So I would like to start to thank you to the organizers for the invitation. My name is Lupe Villegas. I am part of the Visión Optics, a Biophotonics lab in the Institute of Optics in Madrid. And today, as part of the Biophotonics engineering session, we present you optical imaging techniques for sclera biomechanics. So we're going to start. Sclera is the white part of the eye that provides protection to the internal structure and also integrity and rigidity. The sclera is composed of three different layers: episclera, sclera, and lamina fusa. We are focused in the proper sclera that is mainly composed of collagen fibers. So why the sclera is important? In fact, variation in the structure of the sclera is directly related with some ocular disorders. For example, myopia is a change of the axial length of the eye and is directly related with the change in the collagen fiber size. Also, we can show different biomechanical response in healthy and diseased sclera. And also there are different regional variations in the sclera. So how we study sclera? We define zones, and we separate like in temporal, nasal, and superior. So we focus in a specific zone because of the variations. We also identify on animal models. And to do that, I am going to present three different techniques that we are using. The two first technique is using to get a response of the total ocular globe. And in the third technique, we are going to see inside the sclera. So the first technique is airport deformation imaging. So this technique has been used and developed to determine the ocular in a specific the cornea variation and deformation in ex vivo porcine eyes and humans. And in our lab, our current system we implement different functionality. Curatoro and all implement things like, for example, a fast scatter, and also we can change to different cut patterns. As we see, we can use a cross-meridian pattern. So in a specific, what we could do, we use Schwarzschild OCT that acquire different images while we get a puff pulse in a specific zone of the sclera. So we are using for our mission a cross-meridian scan pattern. So we can see in these two, we can measure images in these two meridians. And we are focusing 6 different locations throughout the sclera. As we can see here, we can get the sclera maximum deformation in these specific zones of the sclera. And from the images of OCT, we can also obtain the displacement and velocity response of the sclera in each of these points. We determine the different dynamics of deformations that depends on the sclera regions, the animal model that we are using, and also the interaction between thickness and the biomechanics. Also, we can estimate the properties of the tissue, like Young models, using finite element model simulations, then simulate the stress-strain curve when we can get the Young models. So the second technique I'm going to focus is optical coherence elastography. A way basic coherence elastography have been developed to characterize tissue, and in optics in general, we can determine that with this technique biomechanic response of cornea. So our current system is a coupled piezoelectric actuator coupled to a OCT system. So it means that we have a small probe that is vibrating at 2 kilohertz, and we are taking images during this generation of the waves that going through the scleral tissue. Here we focus also in 4 different zones in the scleral rabbits, and the good thing that have already implemented in that multi-meridian scan pattern. It means that we can measure the wave propagation of the land waves through different directions. In this particular case, we measure through 4 different scans, and we can measure the 8 different directions. So we can get the phase speed and the thickness from our OCT images and from the analysis of the space-time maps. A good thing that we get with that is that the wave propagation speed depends on the scleral location and the direction in all of the zones. Also, we can identify difference between the zones that is close to the limbus in contrast to the zones that is close to the optic nerve. Also, we can also get the shear modulus getting from the Rayleigh-Land equation. Here, we are going to focus inside the sclera to determine the organization of the fibers, the collagen fibers. As we are going to see further in this session, second-harmonic imaging microscopy have been used to determine to visualize fibers in cornea in specific, and to differentiate in different animal models and also humans. So we do that in sclera when the second-harmonic imaging microscopy images are getting by collecting frequency double light generated by focusing an intense coherent light into a tissue. We're going further there in deep, and we can also get light backward and forward. So as we see here with different scleral and collagen images throughout the deep, separated 14 micrometers each other. And we determine here the orientation, how uniform is the direction, and how straight are the fibers using order coefficient and by the analysis of all the images. And also we can estimate the difference between, for example, some regions in the sclera of the rabbits in a specific nasal and temporal regions. So in general, we are using these 3 different techniques to mapping the sclera in a way to prevent and control different ocular disease, as for example, myopia. So I would like to thank to all my bio teams, collaborators, and all the group. Thank you.